Welcome to the course on fundamentals of MIMO wireless communications. Today we will talk about large scale propagation models. The reference books that are to be followed in this particular section would be Wireless Communication by Rappaport. We will usually go by the author's name, and Principles of Mobile Communication by Gordon Stuber. Now, this does not necessarily restrict to these particular books. There are many other books also. These are the particular ones which I have followed and have used extensively in this particular part of the course. Large scale propagation models are basically those which predict the mean signal strength for an arbitrary transmitter receiver separation distance. They are usually used in estimating the radio coverage area of the transmitter. They characterize the signals over large transmitter receiver separation distance. We have seen this briefly in the previous lecture, that suppose there is a transmitter and there are receivers at a certain distance. This particular model is going to predict the power that is received at a distance d from the transmitter to the receiver, and these models are designed in such a way that they capture the fluctuation of signal strength when this d is significantly large, in the orders of hundreds of meters. Whereas, if we move in to the small scale propagation models, they characterize rapid fluctuation of the received signal strength over short interval of distance. We have seen such a figure earlier, where we had the separation distance on the x axis, received signal strength, and there was signal strength fluctuations along the distance, while there was also the average received signal strength that was plotted in red color in that particular figure. So, this average received signal strength is the one which is usually captured by the large scale propagation models, whereas these instantaneous fluctuations are the ones which are captured by small scale propagation models. And the small scale propagation models capture fluctuation over few wavelengths, whereas large scale propagation model captures the fluctuation of signal strength when the separation distance is significantly large. We will see details of such things. Now, large scale propagations are affected by power dissipation, as is here. So, by power dissipation, what we mean is that because of radiation, when there is a transmitter, signals are radiated all across. At the receiver, as we go on at large distance from the transmitter to the receiver antenna size is fixed. So, we are capturing only a small fraction of the big envelope. So, when we are close to this distance, we are capturing a significant fraction of the signal energy, because the globe is like this, whereas when we are far away, we are capturing the same absolute area, whereas the globe has become bigger. So, therefore, you are actually capturing a small fraction of the total energy as you increase the separation between the transmitter and the receiver. These models, they capture the effects of the propagation channel. We will see some of the effects of the propagation channel in few lectures to come. These models assume that path loss at a given transmitter receiver distance, that means there is no shadowing. We will discuss what is shadowing, and it is of course useful in estimating radio coverage area of the transmitter. That means, up to what distance is the received signal strength. The received signal strength as a function of distance is greater than some threshold. Now, when the signal level falls below such a threshold, we say that the receiver is out of coverage. So, as we increase distance from transmitter, transmitter is located here, as we go on increasing the distance up to a certain point in distance d, the signal strength remains above a threshold. So, if this is threshold gamma, the received signal strength decreases, and beyond certain point it decreases below the threshold. So, this region is no coverage region, whereas this region is the coverage region. Such models helps in predicting this distance, the maximum distance of separation. As we have already said, signal strength variation occurs for hundreds or thousands of meters, and beyond within this small distance like 10 to hundreds of meters, there is effect of shadowing, which we will see shortly. Now, these propagation models, as we are talking about and as we have said about models, they could be deterministic or they could be statistical. By deterministic, what we mean is that the signal strength at the receiver can be predicted by solving electromagnetic wave equations. By statistical, what we mean is that there is a significant amount of measured data. From the measured data, there is curve fitting and there is a parametric model, which we will see again shortly. Moving ahead, this particular picture typically represents the fluctuation of signal strength versus distance. Now, if we draw it, things might be a little bit easier. So, if we make receive signal strength P receive as a function of distance, and let us say this is in dBm, this is the separation distance. So, if we consider only large scale propagation models, what we will observe is that the received signal strength almost monotonically decreases with increase in distance, and this is because of the average received signal strength. Whereas, on top of it we will find local fluctuations. We will again see what are local fluctuations, because of which signal strength, the local average fluctuates, on top of which there is instantaneous fluctuation of signal strength, which is the small scale fading. So, in effect, what we get at the receiver is the cumulative effect of these three phenomenon, that is the path loss, the shadowing and the small scale fading, as is represented in this particular slide. So, the tiny fluctuations are due to small scale fading, the slowly varying average as indicated or traced by this cursor is because of shadowing, and the average decrease in signal strength is due to path loss. So, this is the overall phenomenon, and we need to understand these phenomenon. Again, in this part of the course we will focus on these two parts. We will do them briefly and we will spend a significant amount of time understanding the small scale fluctuations. So, we begin with the study of free space propagation models. Now, in free space propagation models, typically examples of such free space propagation models would be satellite links, where between the transmitter and the receiver there is no obstruction. Microwave links, there is line of sight. So, basically in these particular cases we are talking about line of sight, usually indicated by LOS, and here the received power, this is the received power, this is Rx, decreases proportional to Tx Rx separation raised to some power. So, basically if d is the separation distance raised to the power of some exponent, as we will see. So, this is typically in this format. It follows the power law function, and we will use the free space equation to solve the problem and find the expression of received signal strength. Moving ahead, typically if you look at the free space equation, the received signal strength at a particular distance d, as indicated by this expression, is proportional to the transmit power, proportional to the antenna gain of the transmitter, it is proportional to the receive antenna gain, proportional to the wavelength or inversely proportional to frequency, inversely proportional to the distance of separation, and L indicates system losses. So, as described shortly, PT is the transmit power, PRD is the received power at a distance d, where d is the separation between the transmitter and the receiver. GT has indicated transmit power gain, GR is the received power gain, lambda is the wavelength, and AE is the effective aperture. So, if we are to calculate how we are going to get G through this expression, we can find the antenna gain, which is a function of effective aperture of the antenna and which is related to the physical size of the antenna. As you increase the antenna size, your gain increases, but there are of course many details to antenna design. L indicates system losses. Losses would be coupling losses, cables, and many other aspects. So, typically L is there, and a value of L equals to 1 would indicate an ideal system where there is no loss. So, if we go by the free space propagation model, we are going to use this particular equation to calculate the received signal strength at a distance d when the transmitter power is mentioned. If nothing is mentioned regarding the antenna gains, one can assume unity antenna gain. Otherwise, if there is directional antenna, then one has to use the antenna gains corresponding to that particular direction. Right. If we look at this particular model, what we will figure out that the received signal strength is inversely proportional to the square of d. That means, the power decreases 20 dB per decade when expressed in logarithm terms. So, path loss as is an important parameter which will be used. So, path loss is basically an expression which is positive in quantity. This is a very important term. So, it is positive in quantity and it may or may not include the antenna gain. So, when we talk of path loss, it comes from the received signal strength equation with respect to the transmitter as a function of transmitter receiver separation. So, this is a loss expression. Usually, it is the difference between the transmit power and the received power when expressed in the dB domain, and this is because of the path, that is the separation between the transmitter and receiver, that is d. So, this particular variable would be used significantly in predicting coverage for communication systems. Typically, path loss is expressed as shown in this particular equation, that PL in dB, it is usually mentioned in the decibels, is 10 log base 10. This log is usually in base 10. PT, that is transmit power, divided by the received power. So, if you open this up, you are going to get 10 log base 10 of PT minus 10 log base 10 of PR. So, what we have is 10 log base 10 PT minus 10 log base 10 of PR. Usually, PT or PR are given in terms of milliwatts. So, basically what we have over here is dBm, dB in milliwatts. This is also given in dB milliwatts. So, when they are subtracted, what you get, the end result is dB. If it is given in a linear scale, of course, you have PT divided by PR. So, that is the ratio of the transmit power to the received power. So, which would be going into the denominator of the transmit power to calculate the received power. Now, when antenna gains are excluded, that means GT and GR are unity, the equation becomes even simpler. That means, GT and GR have become now unity. Path loss would be 10 log of lambda squared by 4 pi d squared, coming from the free space expression. Now, be careful to note, we have a minus sign, and therefore, inside the log things have got inverted because PT is here. So, an easy way to arrive at this expression would be PT divided by the expression that we have over here is, if we calculate from here, PT divided by PR is equal to 4 pi d squared L divided by GT GR lambda. That is what you see in the next expression. Now, if you put a negative sign, so basically this is 4 pi squared d squared L divided by g t g r lambda squared, and if you take a 10 log 10 and a negative sign, so basically you are doing minus 10 log of, you are putting it to the numerator, g t g r lambda squared divided by 4 pi squared d squared L, and when g t and g r are equal to unity, you have minus log base 10 lambda squared by 4 pi squared d squared L, and that is what you have in the expression in the next slide. So, that is the expression that is available with us, which arrives directly from the free space propagation model. Now, this is a valid predictor for D in the far field of the antenna. This means that we are at a sufficient distance from the antenna and where there are no electrostatic or inductive fields from the antenna. Further, the other important thing which you can see in this particular expression is that in the denominator we have d squared. So, if d takes on the value of 0, then the path loss would go to a very large number. So, this model is not valid for this model. The received signal strength would be infinity when d is 0. So, this model is not valid for d equals to 0. So, there are further improvements which are done in this particular model, and to do this particular improvement, some close in distance d0 has been used. Now, at d0, the received power PR d0 is typically measured. So, that means suppose we are at a distance from the transmitter, if this is the transmitter, this is d. So, if I make it 0, this whole expression is going to fail. So, we will identify some distance d0. At d0, received signal strength at d0 have to be measured a priori. Once this value is available, then the received signal strength can be referenced to this particular d0, because in that case PR d0 is proportional to 1 by d0 squared. Now, d0 is known, PR d0 is known. In order to get P received at d, when PR d0 is given, PR d0 is known, you have to multiply it by d0 and divide by d squared. In that case, this value is known to us. We are simply scaling the distance with these numbers and we will be able to get it. Of course, this d is restricted to be beyond a certain distance, that is d0. So, as is seen in this expression. So, PR d0 may be predicted from the free space propagation loss model. So, basically using the earlier model, we will find out PR d0, and it is measured using average of several readings. So, basically if the antenna is here, we will be averaging at several readings would be taken at d0, and then PR d0 would be calculated. Once PR d0 is calculated, then we can calculate PR d following this particular expression. So, for this it is required that d0 must be greater than df, which is the far field or the Fraunhofer region, but d0 must be sufficiently smaller than practical base station and mobile station distance. What does it mean? It means that the base station is here, this is the d axis. So, we will measure it at certain separation d0 and call it PR d0. This is the reference point. This d0, this should be greater than the Fraunhofer distance, that means it should be in the far field, and d should also be significantly less than a typical BS MS separation distance. I mean, it cannot be very large, it cannot be orders of kilometers. It can be kilometers when base station separation distance would be like few tens of kilometers or so on. So, going by this, what we have over here is PR received signal d is equal to PR d0. Now, remember PR D0 calculation has D0 in the denominator. So, if we multiply by D0, then the D0 and the D0 cancels out. What you are left with is transmit power divided by D squared, subject to the condition that D is greater than D0 and D0 is greater than DF. That means, this particular formula restricts the value of D from acquiring the value of 0, and therefore, rendering the formula useful. Right. So, PR D0 may be predicted using free space expression, as we have said. Now, if we concentrate on the far field region, it can be calculated using the expression here. So, it should be greater than 2 d squared by lambda, where d is the largest linear dimension of the antenna and lambda is the wavelength. So, df is usually calculated in this form, and to be in the far field you have to maintain the criteria that df is greater and greater than d and df is greater and greater than lambda. So, once you have calculated or found out what is df following these expressions, you have to ensure that D0 is greater than df. After you have found this, one has to measure PR D0. Once PR D0 has been measured, that means, this particular value is given and D0 is also given, then we can calculate PRD, that is received signal strength as a function of distance, provided D is greater than D0. For D less than D0, this particular model cannot be used. So, every model has its own limitations and its usefulness. So, we should always remember, when we are taking a model, we are careful with the set of assumption that comes with the particular model. Right. Moving ahead. So, for this particular expression, if we calculate the path loss is given in this expression. Sorry, the received signal strength would be PRD in dBm as the received signal strength in D0 divided by 1 milliwatt plus the logarithm of D0 by D. There was 10 log D0 by D, there was square in the above this 2 has come out. So, instead of 10 log, we now have 20 log. And D0 is typically 1 meter for indoor, around 100 meters for outdoor. It can be 1 kilometer if the separation distance in transmitter and receiver would be few tens of kilometers. Sorry, this particular thing is needs to be corrected. It is not path loss. This is the received signal strength is measured in dBm or dB watt. The received signal strength. Okay. So, as we move further, we go into one of the important models, which is the two-ray model, or and which is a little bit closer to realistic, which is no longer a free space equation. It includes the propagation effects, and this particular model is deterministic, but still it will give us some indication of the received signal strength. So, typical propagation phenomenon that happens when the signal propagates from the transmitter to the receiver, as we have seen in a diagram before, there could be line of sight. We have calculated the expression of received signal strength when there is line of sight. There could be reflection from the ground, there could be reflection from buildings, there could be diffraction from edges, there could be scattering from lamp post and trees, etc., and the cumulative signal comes to the receiver. So, one of the simplest models that we would encounter is the two-ray model, which captures a direct line of sight and a reflected path. Later on, we will see models which captures the different effects as shown in this particular slide. So, this is the famous two-ray model, and it has two rays. So, basically one direct line of sight, one reflected, and it is assumed that this separation distance is very large compared to the height of the transmitter and the receiver. So, there is a transmitting antenna height, there is a received antenna height, and the electric field because of line of sight can be calculated, electric field due to ground reflected ray can be calculated, and the total signal strength at the receiver or the total E field would be vectorial addition of the line of sight as well as the ground reflected ray. So, when these two are added and a whole set of expressions are resolved, what we end up is with the expression as shown in this particular slide here, that the received signal strength is equal to the transmitted power multiplied by transmit antenna gain multiplied by received antenna gain, which we have seen before. Now, we have few more additional terms. We have the antenna height of the transmitter as well as we have the antenna height of the receiver. So, received signal strength as per this formula is dependent upon the transmitter and receiver height, or you can say that this particular model captures the effect of antenna height, because typically we know in general that as you increase the height of the antenna, your signal strength becomes better. So, this is one model which captures some of those effects. Whereas, the most interesting thing as we see that has happened because of the two ray model, that means direct line of sight and the reflected path, is that the denominator exponent, which was d squared, has now become d to the power of 4. Now, what does it indicate? It simply indicates that previously, if the signal strength was falling around 20 dB per decade, now it will fall at 40 dB per decade. So, it falls at a much faster rate than in the free space expression. And what we are seeing is only by taking two rays between the transmitter and the receiver, the received signal strength is now decreasing to the 4th power of t. Now, when there are multiple effects, that means scattering, diffraction and many others, this number will not necessarily be 4, but could be something else. This is one of the very simplistic model which captures somewhat close to reality, and it gives numbers which are quite meaningful, as we will see shortly in some of the results. The path loss expression for the two ray model can be expressed as path loss in dB is 40 log d. This is the separation between the transmitter and receiver, and there is transmitter antenna gain, receive antenna gain, height of the transmitter and height of the receiver. Now, one of the assumptions as mentioned is height of the transmitter and receiver must be much smaller than the separation distance, and also has been indicated by this particular condition. So, this would also indicate that the angles are very small and they are almost at a grazing angle. So, if we look at this expression in actual path loss expression, what happens is this path loss exponent is no longer a fixed value of earlier it was 20, now it is 40, as can be read from this particular expression. In real environments, you can represent these numbers as shown over here, NP multiplied by 10, or we generally write 10 NP. Okay. So, where NP is the path loss exponent, this is the path loss exponent, and it lies anywhere in the range of 1.4 to 6. Now, this is not restrictive at all. These numbers are from measurements, and typically they would lie in the range of 1.4 to 6, as has been observed in many situations. So, if we remember this expression, typically path loss we can say is proportional to separation distance raised to the power of NP, or received signal strength PR at a function as a function of d is proportional to the separation distance raised to the power of minus NP. What you have seen is for free space propagation model, the NP is equal to 2. For two ray model, what we have seen is NP is equal to 4. In practice, this NP can vary between 1.4 and 6 as has been generally observed, but things could go worse on either directions under different conditions. So, we stop this particular lecture in path loss. We continue to study some more effects of large scale propagation model in the next lecture.